September 1909. Tempelhof Field, Berlin. A 15-year-old boy named Alexander Lippisch watches in fascination as Orville Wright pilots his flying machine across the German sky. The demonstration lasts only minutes, but it plants a seed that will grow into one of aviation's most revolutionary concepts. 60 years later, critics who once called his wing designs insane suicide would watch Delta-winged fighters dominate the skies above Vietnam. The Mach 2 Concorde carry passengers faster than sound, and space shuttles glide home from orbit using his principles. They called his wing design insane. Conventional aircraft builders insisted that removing the tail from an airplane was aerodynamic suicide. Military officials declared his tailless concepts too dangerous for operational use. Even fellow engineers questioned whether aircraft without traditional empennage could maintain stability and control. Yet this unorthodox German designer would prove that wings shaped like triangles could outperform conventional aircraft at speeds approaching and exceeding the sound barrier. Alexander Lippisch was born November 2, 1894, in Munich, to an artistic family that seemed destined for anything except aviation engineering. His father Franz was a painter and co-founder of the Berlin Secession movement. His sister Bianca followed the family tradition into landscape painting. Alexander initially planned to attend art school and pursue his father's profession until World War I interrupted his plans and changed the course of aviation history. During his military service from 1915 to 1918, Lippisch served as an aerial photographer and mapper with the German Army. Flying in primitive aircraft over the battlefields of Europe, he observed firsthand the limitations of contemporary aircraft design. The biplanes and triplanes of the era suffered from excessive drag created by their multiple wing structures, wire bracing, and external components. Lippisch began to envision aircraft that could achieve higher speeds and better performance through more efficient aerodynamic configurations. After the war, Germany faced severe restrictions under the Treaty of Versailles that prohibited the development of powered military aircraft. These limitations forced German aviation enthusiasts to focus on glider development, inadvertently creating the perfect environment for Lippisch's radical experiments. In 1918, he joined the Zeppelin Company as an aerodynamicist, where he first became seriously interested in tailless aircraft configurations that promised reduced drag and improved efficiency. Lippisch's theoretical work convinced him that conventional aircraft design was fundamentally flawed. Traditional airplanes required separate surfaces for lift, control, and stability. The wing provided lift. The horizontal stabilizer in the tail maintained pitch stability. Vertical rudders controlled directional movement. Elevators managed climbing and diving. This multiplicity of surfaces created drag that limited performance, especially at higher speeds where drag increased exponentially. His revolutionary insight was that a properly designed wing could perform all these functions simultaneously. A triangular wing with appropriate control surfaces along its trailing edge could generate lift while providing stability and control. The key was understanding how to distribute weight, balance centers of pressure, and design control systems that worked harmoniously within the wing structure itself. In 1921, Lippisch collaborated with friend Gottlob Espenlaub to build his first practical design, the Lippisch-Espenlaub E2 glider. This aircraft featured swept wings and no tail surfaces, representing a radical departure from conventional glider design. Critics immediately declared the configuration unstable and dangerous. Aviation authorities refused to certify the aircraft for flight testing. Insurance companies declined coverage for what they considered experimental suicide machines. Despite official opposition, Lippisch persisted with flight testing that proved his theories were sound. The E2 glider demonstrated stable flight characteristics and performance superior to conventional designs. More importantly, it established the foundation for a research program that would produce over 50 innovative aircraft designs throughout the 1920s and 1930s. Lippisch's growing reputation as an innovative designer led to his appointment in 1925 as director of the Rhön-Rossitten Gesellschaft, Germany's National Gliding Organization. This position provided him with resources, facilities, and talented pilots willing to test his increasingly radical concepts. The organization grew to over 60,000 members, creating a substantial base of support for experimental aircraft development. During this period, Lippisch developed his systematic approach to aircraft design that prioritized practical testing over theoretical calculations. He would first build scale models to test basic aerodynamic principles. Successful models would be followed by full-scale gliders for manned flight testing. Only after proving the concept thoroughly would he proceed to powered aircraft development. This methodology was revolutionary in an era when most designers relied heavily on wind tunnel data and mathematical calculations. From 1927 onwards, Lippisch concentrated on a series of tailless designs designated Storch 1 through Storch 9. The Storch series featured swept wings and represented systematic exploration of tailless aircraft configurations. Each design incorporated lessons learned from previous aircraft while testing new concepts for stability, control, and performance. The aircraft appeared fragile to observers accustomed to conventional designs, but flight testing proved they were robust and reliable. The Storch series represented Lippisch's methodical approach to solving the fundamental problems of tailless flight. Traditional aircraft relied on horizontal stabilizers to maintain pitch stability, but Lippisch discovered that properly designed wings could maintain stability through careful attention to the center of gravity and center of lift relationships. The key was positioning the aircraft's weight distribution to create natural stability without requiring separate tail surfaces. Each successive Storch design refined this concept through incremental improvements. The Storch 1 established basic feasibility of swept-wing tailless flight. The Storch 2 improved control authority through modified elevon designs. The Storch 3 explored different sweep angles and aspect ratios. By the time development reached the Storch 4, Lippisch had created an aircraft that surpassed conventional gliders in both performance and handling characteristics. The lightweight construction that made the Storch series appear fragile was actually a sophisticated engineering achievement. Lippisch used advanced materials and construction techniques to create structures that were both light and strong. The aircraft featured fabric-covered wooden frameworks built to tolerances that exceeded contemporary manufacturing standards. This attention to detail was essential because tailless aircraft required more precise construction than conventional designs to maintain proper balance and control. In 1928, Lippisch achieved a historic aviation milestone when his Ente design became the world's first rocket-powered aircraft. Fitted with solid-fuel rockets developed by Fritz von Opel's team, the tailless glider demonstrated that unconventional designs could incorporate revolutionary propulsion systems. The flight lasted only minutes, but it proved that rocket power and tailless configurations were compatible for future development. The Storch series culminated in 1929 with the Storch 4, which demonstrated impressive stability and control characteristics during demonstrations at Tempelhof Field in Berlin. Günther Grönhoff, one of Germany's most skilled test pilots, flew the aircraft with confidence and praised its handling qualities. The demonstration impressed aviation enthusiasts, but failed to generate government funding for further development. However, the Storch series convinced Lippisch that delta wings offered superior characteristics for high-speed flight. Delta configurations provided greater structural strength than straight wings while maintaining the aerodynamic advantages of tailless design. The triangular shape distributed loads more efficiently and offered better control authority at high speeds, where conventional control surfaces became less effective. Between 1931 and 1939, Lippisch developed his famous Delta series, numbered Delta 1 through Delta 5. These aircraft represented the first successful pure delta wing designs in aviation history. The Delta 1 glider achieved its first flight in June 1931, with Günther Grönhoff at the controls. The successful flight demonstration at Tempelhof Field proved that delta wings could provide stable, controllable flight characteristics. The Delta series attracted attention from military officials who recognized the potential advantages for high-speed fighter aircraft. Delta wings offered superior performance at high speeds, where conventional designs suffered from compressibility effects and control problems. The triangular configuration provided excellent roll control through elevons on the wing's trailing edge, while maintaining pitch and yaw stability without traditional tail surfaces. However, the Delta IV project encountered serious problems when Gerhard Fieseler attempted to build a powered version as the F-3 Vespe. Fieseler's aircraft proved highly unstable and crashed during initial flight testing. The failure reinforced critics' arguments that tailless designs were inherently dangerous and unsuitable for operational use. German aviation authorities seriously considered banning further development of Lippisch's concepts. Professor Walter Georgi of the Deutsche Forschungsanstalt für Segelflug rescued the program by securing funding from the Reich Air Ministry to purchase the crashed aircraft and continue development. Under Lippisch's direction, the aircraft was rebuilt as the Delta IVA, with significant modifications that eliminated the stability problems. The redesigned aircraft demonstrated excellent flight characteristics and validated the Delta wing concept for future development. Wind tunnel research conducted in 1939 revealed that Delta wings offered significant advantages for supersonic flight. The triangular configuration maintained effective control authority at high speeds, while avoiding the shockwave problems that plagued conventional wing designs. This discovery convinced military officials that Delta wings represented the future of high-speed fighter development. In early 1939, the Reich Aviation Ministry transferred Lippisch and his entire design team to Messerschmitt's factory in Augsburg to develop a rocket-powered interceptor around Helmuth Walter's revolutionary rocket engines. The team adapted their most recent design, the DFS-194, for rocket propulsion, creating what would become the Messerschmitt Me-163 Comet. The Me-163 represented the culmination of Lippisch's 2 decades of research into tailless aircraft design. The rocket-powered interceptor featured a pure delta wing configuration with no tail surfaces whatsoever. All control functions were performed by elevons along the wing's trailing edge. The design achieved unprecedented performance, reaching speeds over 600 miles per hour in level flight. The development of the Me-163 encountered numerous technical challenges that tested Lippisch's engineering skills. The Walter rocket engine produced enormous thrust, but consumed fuel at an alarming rate, limiting flight endurance to only minutes. The corrosive rocket propellants posed constant danger to pilots and ground crews, requiring extensive safety procedures and specialized handling equipment. Most critically, the aircraft's high landing speed made it extremely difficult to operate from conventional airfields. Lippisch solved these problems through innovative design solutions that demonstrated his mastery of aerodynamics and engineering. The delta wing configuration provided excellent low-speed handling characteristics that conventional wisdom claimed were impossible for tailless aircraft. Special flaps and control surfaces gave pilots the authority needed for safe approaches and landings. The aircraft's compact design minimized weight while maximizing structural strength to withstand the stresses of rocket-powered flight. The Me-163's operational history revealed both the potential and limitations of Lippisch's concepts. The aircraft could climb to 30,000 feet in under 3 minutes and intercept Allied bombers at speeds no conventional fighter could match. However, the brief powered flight time meant pilots had only one chance to attack enemy formations. If the first pass failed, the aircraft became a vulnerable glider requiring immediate landing at the nearest airfield. Test pilot Heini Dittmar achieved spectacular results flying the prototype, Me-163. On October 2, 1941, he reached 623.85 miles per hour, officially breaking the world speed record. The flight demonstrated that tailless aircraft could achieve performance levels impossible with conventional designs. More importantly, it validated Lippisch's theories about high-speed flight characteristics. However, friction developed between Lippisch and Willy Messerschmitt over the aircraft's development. Messerschmitt disliked the unconventional design and resented that he had not been involved in its creation. Technical disagreements about production methods and operational requirements created tension between the two strong-willed engineers. By 1943, their relationship had deteriorated to the point where collaboration became impossible. Lippisch transferred to Vienna's Aeronautical Research Institute in 1943 to establish his own independent design bureau focused on high-speed flight research. Free from corporate constraints, he concentrated on developing advanced concepts for supersonic aircraft that would surpass even the revolutionary Me-163. His most ambitious project was the P-13A, a delta-winged interceptor powered by a ramjet engine. The P-13A represented Lippisch's vision of the ultimate fighter aircraft. The design featured a pure delta wing optimized for supersonic flight, with a ramjet engine that would provide enormous thrust without the complexity and weight of conventional power plants. The aircraft was intended to intercept Allied bombers at speeds exceeding the sound barrier, making it virtually untouchable by enemy fighters. However, wartime conditions prevented completion of the P-13A project. Allied bombing raids disrupted development work and destroyed prototypes under construction. On June 16 and 24, 1944, American bombers attacked Vienna, destroying the factory where the prototype was being built, and killing over 40 of Lippisch's colleagues. The advancing Soviet army forced evacuation before the project could be completed. Nevertheless, Lippisch's research into supersonic delta wing design had profound implications for post-war aviation development. His theoretical work established the aerodynamic principles that would guide fighter development throughout the jet age. The delta wing configuration became the standard for supersonic interceptors, attack aircraft, and even civilian transportation. After Germany's surrender, American technical intelligence teams recognized the value of Lippisch's research and recruited him under Operation Paperclip. Along with other German scientists, he was brought to the United States to continue his work on advanced aircraft design. The transfer of his knowledge and experience would prove crucial for American aviation development during the emerging Cold War. Convair Corporation became particularly interested in Lippisch's delta wing concepts for their planned F-92 fighter project. To gain experience with delta wing handling characteristics, they first built the 7002 test aircraft, which on June 9, 1948, became the first jet-powered delta wing aircraft to fly successfully. The test program validated delta wing performance at high subsonic speeds. The success of initial testing led to development of the XF-92A, a pure delta-wing research aircraft that explored handling characteristics at transonic and supersonic speeds. Although the Air Force ultimately canceled the F-92 fighter program, the research data proved invaluable for subsequent delta-wing aircraft development. Lippisch's design principles were finally being validated on a large scale. The Convair F-102 Delta Dagger became the first operational delta-wing fighter to enter squadron service with the United States Air Force in 1956. The aircraft demonstrated the superior performance characteristics that Lippisch had predicted decades earlier. Delta wings provided excellent high-speed handling, rapid climb rates, and superior maneuverability at altitude compared to conventional fighter designs. The success of the F-102 led to development of the even more advanced F-106 Delta Dart, which entered service in 1959. This interceptor aircraft achieved speeds exceeding Mach 2 while maintaining stable flight characteristics and effective control authority. The delta wing configuration had finally achieved the performance levels that Lippisch had envisioned during his early experiments. Perhaps the most spectacular vindication of Lippisch's concepts came with the Convair B-58 Hustler, the world's first supersonic bomber. This delta-winged aircraft could cruise at Mach 2 while carrying nuclear weapons, representing the ultimate expression of Lippisch's vision for high-speed military aircraft. The bomber's sculptural beauty and revolutionary performance proved that delta wings were not merely functional, but could create aircraft of extraordinary elegance. Beyond military applications, Delta Wings found success in civilian aviation with the Anglo-French Concorde supersonic transport. This aircraft carried passengers at twice the speed of sound using the same delta wing principles that Lippisch had developed in his glider experiments decades earlier. The Concorde's 27-year operational career demonstrated that delta wings could provide safe, reliable service in commercial aviation. The Concorde program validated Lippisch's early predictions about delta wing advantages at supersonic speeds. The triangular configuration maintained structural integrity under the extreme thermal stresses of Mach 2 flight, while providing the stability and control characteristics necessary for passenger operations. The aircraft's distinctive shape became an icon of advanced technology and represented the pinnacle of supersonic transport development. Soviet aircraft designers also adopted Lippisch's delta wing concepts for their most advanced fighters. The MiG-21 became one of the most widely produced fighters in aviation history, with over 13,000 aircraft built using delta wing configurations. The success of Soviet delta wing fighters in combat operations around the world validated the universal applicability of Lippisch's design principles. The proliferation of delta wing designs during the Cold War demonstrated that Lippisch's concepts transcended national boundaries and political systems. Both NATO and Warsaw Pact nations developed successful delta wing aircraft that dominated their respective air forces. The configuration became synonymous with advanced military technology and represented each nation's commitment to maintaining air superiority through superior aircraft design. French aviation embraced delta wings with particular enthusiasm, producing a series of successful aircraft including the Dassault Mirage family of fighters. These aircraft achieved remarkable export success, with delta wing Mirages serving air forces worldwide. The configuration's combination of high performance, structural efficiency, and operational flexibility made it ideal for diverse missions from air superiority to ground attack. Even space exploration benefited from Lippisch's pioneering work. The Space Shuttle used a delta wing configuration for atmospheric flight during re-entry and landing. The triangular wing provided the stability and control characteristics necessary for unpowered gliding from orbital speeds to runway landings. Lippisch's principles, developed for simple gliders in the 1920s, proved applicable to spacecraft returning from the edge of space. Swedish aircraft manufacturer Saab developed a series of innovative delta wing fighters including the Draken, Viggen, and Gripen. These aircraft demonstrated that delta wings could provide exceptional performance for smaller air forces with limited resources. The configuration's structural efficiency and maintenance advantages made it particularly attractive for nations operating modest fighter fleets. Modern military aircraft continue to incorporate delta wing principles in various forms. The Eurofighter Typhoon, Dassault Rafale, and other contemporary fighters use modified delta configurations that blend Lippisch's original concepts with modern aerodynamic refinements. These aircraft achieve performance levels that would have seemed impossible during the early days of aviation. Contemporary delta wing fighters incorporate advanced materials, computer-controlled flight systems, and sophisticated aerodynamic refinements that Lippisch could never have imagined. Carbon fiber construction provides strength-to-weight ratios far superior to the wood and fabric structures of his early gliders. Fly-by-wire control systems enable aircraft configurations that would be impossible for human pilots to control manually. Yet the fundamental principles of delta wing aerodynamics remain unchanged from Lippisch's original discoveries. The influence of Lippisch's work extends beyond traditional aircraft to modern unmanned systems and experimental vehicles. Military drones increasingly employ delta wing configurations for their combination of stability, efficiency, and stealth characteristics. Research programs investigating hypersonic flight rely heavily on delta wing principles for vehicles intended to operate at speeds exceeding Mach 5. Lippisch himself continued his research in the United States until his death in Cedar Rapids, Iowa, on February 11, 1976. His later work included ground effect vehicles and unconventional aircraft concepts that pushed the boundaries of aerodynamic knowledge. Though he never achieved the commercial success of other famous aircraft designers, his influence on aviation development was immeasurable. The transformation from experimental glider configurations in the 1920s to operational supersonic fighters within 3 decades represents one of aviation's most remarkable technological progressions. Lippish's persistence in developing concepts that others considered impossible led to fundamental changes in aircraft design philosophy that continue to influence modern aviation. Today, delta wings are so common in high-performance aircraft that their revolutionary origins are often forgotten. The configuration that critics once called insane suicide has become synonymous with speed, agility, and advanced technology. From military fighters to civilian transports to space vehicles, delta wings dominate applications where performance takes priority over conventional design practices. The legacy of Alexander Lippisch extends beyond specific aircraft designs to encompass a fundamental shift in engineering philosophy. His willingness to challenge conventional wisdom and test radical concepts through systematic experimentation established methods that modern aerospace engineers still follow. His emphasis on practical flight testing over theoretical analysis revolutionized aircraft development procedures. The young boy who watched Orville Wright fly over Berlin in 1909 could never have imagined that his inspiration would lead to aircraft capable of flying faster than sound. Yet Lippisch's journey from artistic family background to revolutionary aircraft designer illustrates how individual vision and persistence can transform entire industries. His insane wing design had become the foundation for some of aviation's greatest achievements. The suicide configuration had proven safer and more effective than conventional alternatives. German fighters had indeed become untouchable in the sky, not because of the specific Me-163, but because delta wing principles had evolved to create aircraft that dominated aerial combat for generations. Alexander Lippisch's triangle-shaped wings had conquered the heavens and reached toward the stars.